Hello everyone, my name is Martin Jones and I'm the project manager for the Coastal Erosion from Space project. I'm going to spend the next few minutes introducing the project, some general principles on Earth observation, and I do apologise for any scientists in the audience, but I think it would be useful for everybody's understanding if we have a common place to start from. And then I'll hand over to the team who will describe our processes, the ones we've developed, and also use examples of products from those processes. So why are we doing this project and what has been the response from the European Space Agency? Who are the Coastal Change Consortium and what has been our approach? So the problem has been that climate change is now placing a lot more energy into the system, and with this extra energy comes the greater risk of larger storm events, which will be occurring much more frequently. The risk to coastal flooding and erosion is increasing, and at the same time more and more infrastructure is being built along the coasts. And in addition, certain economies are reliant on tourism, which requires those pristine beaches to actually be sand filled, and this often involves very expensive resupply of sand. Our ports and our harbours are increasing their traffic, and they need waterways clear for the vessels that come in and out, and this means more dredging and more dumping. And around the world, the natural coastal defences, such as the salt marshes and the mangrove, are being depleted at a staggering rate. The cost of field surveys, i.e. walking along the patch, seeing what you can see, these are becoming increasingly more expensive. But more importantly, the ability to recreate a field survey of information going back 25 years over these large areas that we're interested in is simply not possible. So to address these problems, the European Space Agency, ESA, has posed the question of what can be achieved by using space-based assets, and especially the high-resolution and exceptionally well-calibrated Sentinel mission satellites. The task is not simply one of pure academic research or just a feasibility study, but it's one of establishing a pilot service that can deliver products covering at least 1,000 kilometres of coastline, but also in a range of different geomorphological sites across at least 3 nations, but looking back for that 25 years. So to achieve this, ESA have divided the project into 2 phases. There's a feasibility phase, and that's been followed by an implementation phase. And we're now approaching the end of this second phase with about 20 months gone as a team. And we've been capturing the requirement, we've been refining the pure need into what can be achieved with the current technology, and we've been designing and developing and testing products and assessing their reliability and their worth. So the consortium is a collaboration between a service provider group, and they are delivering the optical products and the project management, which has been delivered by us in ARGANS, the radar feasibility in its research and the production, which has been delivered by our partners Landsat, and then these 2 groups are being brought together to have their data stored by the data processing and storage capability provided by the EO Data Centre Advisio, which is in Luxembourg. The user group, that comprises IH Cantabria from Spain, the British Geological Survey, the Geological Survey of Ireland, and Arctus in association with the University of Quebec at Rimouski, and they've conducted the validation and the assessment of the product's utility based on their expert knowledge and their comprehensive user requirement research. So working together as partners, we have not only established a collaboration with the national experts, but we've also enabled the project to deliver over many geomorphological types. We've covered 15 sites in 4 countries, and the project is covering well over 2,000 kilometres of coastline, and that goes back to 25 years. So our approach. Our approach is pretty simple in conceptual terms. We've improved the positional accuracy of the imagery to within 3 metres on the ground. We've derived every available waterline for the past 25 years, and we've derived continuous shorelines based on the local tidal datums employed, and we've also used the best available auxiliary data. So before I go on too far, there are surprisingly no internationally agreed terms that are commonly used for the various land-sea boundaries. So I'm just going to define the ones that we're using in this project, and then we can use the same ones throughout. So for the waterline, that's the edge of the sea at the snapshot in time. And that means it's the limit where the tide is at that moment, or when the satellite is directly overhead. The shoreline, that is a prediction of where the tidal waterline would be at a determined time, i.e. mean high water springs, or highest astronomical tide. A littoral line, that's the high water line depicting a hard boundary where there's a fixed object in the way of the tide reaching its high water, such as a seawall or a cliff. And finally, the time series, which is a derived product based on a series of different shorelines or a series of different waterlines. The depth of closure is described for us as the depth beneath which erosion is not considered to be significant. So I'm now going to go on take you through some general principles outlining the key differences between the synthetic aperture radar that we use and the optical sensors on board the satellites. And as I stated at the beginning, this is not going to be a deep technical lecture, it's just going to be a few basics, but the key message is that neither system is perfect, however they are very complementary, as you will see. So Sentinel-2 and Sentinel-1, these are the main missions that we've been using. Sentinel-1 is an active radar system and Sentinel-2 is a passive multispectral or an optical system. And as you can see, these were launched about 5 years ago. To go back to the 25-year point, we're also reliant on older satellites such as the USGS NASA Landsat mission. However, with the older satellites, you do get less resolution on the ground, so we just need to be mindful of this. The Sentinel mission have a refresh rate, i.e. passing over the same bit of ground every 5 to 6 days, whereas the Landsat older mission revisits the same patch every 16 days. But the great thing is that they do revisit the same spot at the same time of day, which really helps with comparisons of fixed objects over time. There are daily tidal changes to the sea state and to the sea level, and of course these create a different set of problems, of which we'll talk about more later. I've now got a short video clip which enables you to see how the satellites collect data as the Earth spins. I think it's pretty nice to see this video, but it really gives the idea. And as you can see, there are two satellites which are both orbiting the Earth, but also I think it shows you that we also get pretty much a global coverage. So just to recap, so there are currently 2 satellites in both Sentinel-1 and Sentinel-2 mission, and there are further launches planned in the coming years. So what can we see? And that of course depends on the resolution. Commercial satellites, as you can see, the WorldView Maxar satellite on the left, these have been around for the last few years and they've got a 2-meter resolution. But this comes at a huge price. It doesn't have the imagery available over all the places that we want for all of the time, and it's certainly not affordable for the whole of the 25-year study of this project. Landsat 5, though, is providing a 30-meter resolution, but it is free to use and it does go back that 25 years. However, the advent of the Sentinel mission has introduced 10-meter resolution, and this is perfect for looking at coastal change. The positional accuracy of each of its pixels is about plus or minus 12 meters onto the ground. However, shortly we'll explain what we have done to greatly improve this accuracy to be more appropriate to the type of erosional or accretional changes that occur. I'm now going to go on to the key differences between the optical sensors and the radar sensors, and that's basically the energy source. So for the optical missions such as Sentinel-2 or Landsat 5 and Landsat 8, the energy source is the sun. i.e. they are passive receivers and the sensor receives sun reflections pretty much like our eyes. However, we can only see the visible spectrum, but Sentinel-2 also sees many infrared bands that we humans just simply cannot see, but these are vital for when we're looking for the land-sea boundaries. The SAR, or the Synthetic Aperture Radar mission, on the other hand, provides its own energy source in the form of a microwave or a radar pulse, i.e. they are an active sensor. And it must be noted that the pulse transmitted is from the right-hand side of the satellite, and these pulses are reflected back to the satellite when the Earth's surface is rough. So the rougher the surface, the stronger the return, or the brighter the pixel appears on the image. So a calm sea that will therefore reflect the energy away from the sensor would leave a black picture. So this means that our eyes can recognise the optical image that's shown here on the left, but we only see a black and white image on the picture on the right, the radar picture on the right, and that shows the strength of return from the pulse that's reflected back. So the black part is where the pulse has been reflected away, and in this case it's the sea. So the next 2 images have been taken a few months apart, and for all intents and purposes they're the same thing, they're very similar. However, when we zoom in, you can see that there's a light group of pixels, which is an object, and they have moved relative to that little red cross, which is a real position on the ground. And the reason is that the Sentinel-2 mission performance delivers a pixel to within plus or minus 12 meters on the ground. So to increase this accuracy with the repeatability, we've used a geolocation processor to co-register each image, and you'll hear more about this later. However, this repositioning of every pixel is vitally important when trying to compare small changes over time. And what we're very keen to determine is whether any change we observe is due to a positioning accuracy difference or is actually due to the real change on the ground. So for optical images, the key limitations present when the sunlight is prevented from returning to the satellite, i.e. when there's cloud or when it's nighttime. And this image shows a perfect day on the left, and then the same location on a cloudy day on the top right, and a radar image taken within a few minutes of the top right image is in the bottom right. So too much sunlight reflected also can give problems, can give glint from the sea or an overexposure, and also the atmospheric conditions can make a big difference. But I think the real point to note is the top right image is just a complete whiteout, and therefore there's no detail that you can use of any good. For the radar imagery, due to the transmission of the pulse firing from that angle on the right-hand side of the satellite, there is a geometric distortion or a difference in the image's view on the ground between the ascending orbits and the descending orbits. And in addition, as these reflections are based on the smoothness or roughness of the surface, there can be some ambiguity as to what exactly is being reflected. So just for some examples, on this side, you can see that there on the top left-hand slide, there's a row of trees and they've got a very, very large shadow behind them. That shadow would be even larger if it was a huge cliff along a coastal boundary. On the top right-hand slide, there's a piece of land and a bay, and there's a bright star in the middle, and that's the reflection from a ship. And then the bottom central image is on a very rough day, so the sea is actually reflecting back this time to the satellite receiver, and therefore it makes the land-sea boundary very, very difficult to see. However, the aim is to play on the strengths of both technologies and to obtain a comprehensive series of picture and to get them as often as we can over the large geographic range over the large time frame of 25 years. So I'm now going to pass you on to the team who will describe how the processes have been developed and the products that they deliver. Thank you very much indeed.